Hey there, welcome back to Abstract Algebra. This is the first of what will be three of these video lectures for the material that we're going to cover in Chapter 3. Chapter 3 is all about the symmetric group, so that's kind of good news because the material in this section is not totally new. So let's get right to it. In this first lecture, we're going to talk about the material in section 3.1, and really what my goals in this lecture is to reintroduce the symmetric group Sn. So it's one of our examples we've been talking about, but I want to reintroduce briefly and remind you of some of its properties. And then I want to establish a way to work in Sn that's called array notation. It's going to be a little bit better than just writing out the functions kind of as lists of outputs. And then I'm going to prove one theorem. I'm going to prove that every element of Sn, if you pick a fixed element of Sn, I'm denoting it by the lowercase Greek letter sigma. The author will do the same, lots of lowercase Greek letters to denote permutations. You pick an element of Sn and it induces a certain equivalence relation on the subset of things that we're permuting. All right, so it's kind of a setup for the next time. All right, so let's get right to it so that this doesn't get too long. Let me just remind you, if you fix a natural number, so some number that's at least 1, I'm going to denote by I the set of numbers between 1 and n. And all Sn is, you guys recall, is it's the set of functions from I to I, that is functions from the set 1 to n to itself, but not just any functions, they have to be 1 to 1 and onto. They're bijections, all right? So it's the set of all bijections, or if you like, permutations of the set of numbers 1 to n. That's what the elements of Sn are. Sn is called the symmetric group because it's a group under function composition. So the binary operation is function composition. We'll continue just to write f times g instead of this kind of calculus-based f composed with g for two functions. So when you see f times g, you know that I mean compose the function f with the function g, okay? Just to establish some of our notation, we'll continue to denote identities by E. So the identity here is in particular the identity function. It's the function that sends every element of the set I to itself. And then what's the inverse of a permutation? Well, the inverse of a permutation is the function that undoes f. So if you compose f inverse with f, or I should say it the other way, compose f with f inverse, you get the identity function. Compose it in the other direction as well. Cool. What do we know about Sn? You can ask me about this when we're all online at the same time, or you can check it out in your books or write me an email, talk to me one-on-one. But Sn is a group of order n factorial. There are n factorial permutations of n elements. So it's a finite group, but it gets big kind of fast as a function of n, its order. It's a non-abelian group. Given two permutations, they won't necessarily commute. So f times g is not necessarily g times f. Well, that's true if n is at least 3. There's a couple of small exceptions. I'm going to leave these as exercises to you, but the permutations of 2 elements is actually a cyclic group isomorphic to Z2. So you could try to prove that or ask me about it. And then permutations of 1 element, well, it's a trivial group. There's only one permutation of 1 element, it just fixes the element. So typically speaking, these things, when you're talking about symmetric groups, we don't speak about these two very much. They're sort of different. They're both abelian, cyclic. No other symmetric group has those properties, so they're sort of exceptions. So really, when you're thinking about symmetric groups, most people in the world would be thinking about symmetric groups on a set with at least 3 elements. All right, okay. So let me tell you what I mean by array notation. I think we've talked about this before, but I don't know if we ever gave it this name. So when you write a permutation in array notation, you're going to write this sort of 2 rows of numbers. The first row of numbers is always just the set, the elements in the set I, the indices, I'll call them, in order, always writing them in order, 1, 2, 3, and so on. And then below each index, you write the image of it under your permutation. So the number that I'll write below 1 is f of 1. The number that I write below 2 is f of 2, and so on. So the second row in the array is the outputs, and looking at an array if it defines a permutation, because the second row should be the numbers 1 to n in some order. Yeah, so the numbers 1, 2 up to n in some order. Every one of them is there, nothing's missing, but they don't have to necessarily be in some order. F has permuted them. All right. So just to get used to it, we've worked a lot in the group S3. Let's list the 6 elements of S3. I've started the work a little bit so the video doesn't get too long. Over here, I've got the identity. The identity permutation sends 1 to 1, 2 to 2, and 3 to 3. Yeah. So the number below each one of the inputs is the input. That's what the identity function means. I'm going to try to use some consistent notation with what we did in the past. So I'm going to write down this element that I've called F. F is the permutation that sends 1 to 2, it sends 2 to 3, and it sends 3 to 1. So I can write that down in that array notation like that. Yeah. I used to sort of just draw this in these dot notations. 1 goes to 2, 2 goes to 3, 3 goes to 1. So the array notation is just sort of it's an alternative to that where you're labeling everything. Same idea. I'm just going to list all 6 of them. I'm not going to give them names here for a second other than this. Well, let's do this one, G. G, we always called the permutation that sends 1 to 2, it sends 2 to 1, and it sent 3 to itself. Yeah, you can draw it, but I'm going to write it in array notation. And then I'm just going to write the other ones here. We would have 3, 1, 2 is a possibility. There's the permutation that interchanges 1 and 3 and fixes 2. And there's the permutation that fixes 1 and interchanges 2 and 3. And you can stop the video if you like, but and try to count. But I've got 6 different permutations here. I know 3 factorial is equal to 6, so I know I've got all of them. All right, so there's the 6 elements of S3 in array notation. Let's make a couple of computations here. Compute in S3. You can see I've got a little warning here for you that function composition is performed left to right. Yeah. So when we do this product, we're going to complete it over here in a second, but the function that's going to go first is the one that's written on the right. That function goes, and then the function on the left. When we compose functions, we do it right to left. Yeah. Okay, so how are we going to do this? How are we going to compute this product using these array notations? And by the way, if you look at what permutations I have written here, do they have names up above? This first one looks like it's our F up there. Yeah, F is the permutation 2, 3, 1 in the second row. And what's this one? This is G. So really what I'm computing is G times F. I'm computing G times F in the group S3. So how do you do that? Well, you have to do it one element at a time. So looking at this input 1, I have to see where it goes under the composition. So let's just follow it. The first function to go here is F, and F sends 1 to 2. Yeah, that's what that array notation means. So that 2 then is going to get plugged into G. So I'm looking at the top row in G, that's a 2, and I see that it gets sent to 1. So when it's all said and done, the 2-step process sends 1 to 1. Yeah. You can stop the video and see if you can fill the rest in. I'm just going to say them. So looking at the next input, 2, it's the one I want to do next. F sends 2. Oops. F sends 2 to 3. G sends 3 to 3. So at the end of the day, 2 went to 3. You can check it. 3, F sends to 1. 1 goes to 2. So 3 goes to 2. All right. And looking back up here, that's one of the 6 we wrote. Of course it is. It's right here. That's GF. Oops. It's GF. I'll let you check it out on your own, that if you compute F squared and then take its product with G, you'll get that one. And this one itself is F squared, F times itself. So you can kind of do some more exercises like we just did there to get those 6 elements. And that's how we've written down S3 this whole semester. Yeah, we've written down that S3 is the identity. There's this function F, it had order 3. There's this function G that has order 2, and then we have the product of G with F and the G with F squared. That's how we've written down this group the whole semester. Cool. Let's practice a little bit more here. In the second example, I've got set up. I didn't name these things, but I've got some permutations in S5. All right, so if you want to give them names, well, we could write the names above them, but these arrays define them, and I want to compute this composition. I want to compute this composition, so I want to know, well, what element of S5 is this thing? Yeah, I'm going to write my final answer sort of spot down here. I know that a permutation in S5 permutes the 5 elements, so I want to know, well, which ones? I want to know what should we be writing in the second row of this array down here. But before we can do it, one of these permutations is written as the inverse of the array that we're looking at. So I want to start off by kind of rewriting that thing. So I'm going to have to do a little copying here, and to keep the video shorter, I'm going to copy a little bit faster than I can write. I'm just going to kind of bring those guys down here. And then how do you write down the inverse of a permutation? So I want to simplify this thing over here. So I'm just looking at this last permutation. Let me color it in yellow. All right. So if I'm trying to find the inverse of that thing I just colored in yellow, I have to be thinking of the inputs, right? Inverse is switch input and output. So looking at that row that's colored yellow, I can see the 1 down there, and above it is the 1. So the inverse function must also send 1 to 1. All right. Now look at the 2. I'll underline it so I don't have to switch the pen. In that function that's written there, 5 goes to 2. So in its inverse, 2 goes to 5. All right, does it make sense what I'm doing? 3 has to go to 2 because above it, 2 went to 3. So when you're looking at the inverse of a permutation, you basically have to look at the numbers in the bottom row and see what's above them. Those numbers in the bottom row aren't going to be in order. Okay, so there's the inverse of our permutation written out. It sends 1 to 1, 2 to 5, 3 to 2, 4 to 3, and 5 to 4. So that's how you can invert something in array notation. You have to kind of swap the bottom and top row, but you have to do that in a way that the new top row goes in order. And now let's just do it. I'm going to kind of highlight one of these things as I speak about them, and then we'll just kind of try to fill it in. You can stop the video and then you can ask me about it in class. But working right to left, that's the important part to remember. What I have to do is something like this. Just watch the screen for a second to see the colors. I'm wondering where 1 goes. Yeah, that's the first element that I'm trying to fill in down here. So I look up here and I go, well, 1 goes to 1. Okay, fine. Then I look to the next function to go, it sends 1 to 2. Then I look at the last function, which sends 2 to 1. And believe it or not, when we're all done, 1 has gone to 1. Let's try it again. Let me pick a different color. Let's try to find out where 2 is going to go. Okay, well, in the first function to go, 2 gets sent to 5. But then 5 gets sent to 1, and 1 gets sent to 3. So at the end of the journey, 2 got sent to 3. Does it make sense? I've got more colors. We can do it again. What do you like here? How about this light green? I'm wondering what happens to 3. Well, 3 goes to 2, which goes to 3, which goes to 5. So 3 went to 5. All right. You got it? Wondering what happens to 4. 4 went to 3. 3 goes to 4. 4 gets fixed. So at the end of the day, what happened to 4? It went to 4. Got fixed. Last one is 5. You can check it, certainly, but look at the bottom row in our answer over here. The only thing that's missing is 2. So we better get a 2. Do I have one more fancy color here? Maybe we'll go for something like orange. Yeah, so I'm wondering what happens to 5. 5 goes to 4, which goes to 5, which goes to 2. So sure enough. Okay, so there's some more practice. Some more practice computing these things. One more, just to illustrate that if you're just given one permutation, sigma, you want to compose it with itself. Well, it just means, or take its square rather. It means compose it with itself. Let me do that again. the wheels are coming off here. That went to 2. All I wanted was this thing, because I just want to stack it next to itself. This came out better in the rehearsal. Can you stop it, the video, and compute this yourself, and then just look back and see if you got the same answer? Yeah, I won't do all the color coding this time, although I hope you do like it. Let's see how this works. Composing this, again, right to left. You got to start on the right. So 1 goes to 3, which goes to 1, so 1 is fixed. Then we have to do 2 goes to 4, which goes to 2, so 2 is fixed. 3 goes to 1, which goes to 3, so 3 is fixed. 4 goes to 2, which goes to 2, so 4 is fixed. So it looks like sigma squared is actually the identity. So it's the order of sigma is 2, if you like. The order of sigma is 2. Some of your homework problems are going to ask you to find the order of a permutation. You know what that means. Compose that permutation with itself until you get the identity. And I hope you have a small order so you don't have to compute it so much. All right, so that's the, let me just, sorry to make you dizzy, scroll back up here. We have done 2 of our 3 tasks. We've introduced the symmetric group, or reintroduced it rather. I've shown you how to write array notation and hopefully pushed you down the path of where you'll be able to practice writing those arrays yourself, getting used to computing in this very important group. So the last thing to do here is to state and prove this theorem. Again, this theorem is going to seem a little bit out of the blue. I'm setting up something for next time when we start talking about something called cycle decomposition. All right, so I've got the statement of the theorem written here, but I'm going to write out the proof as we go, maybe making it a little bit easier pace to follow. Okay, so what is our theorem? Our theorem says that if you take a natural number n and you take a permutation sigma in Sn, then I'm going to define a certain relation. I'm going to define a relation tilde on the set of indices. So the set that I'm defining the relation on is the set of things that I'm permuting. And here's how it works. Okay, 2 indices, I and j, I'm denoting them. They're going to be equivalent if you can find some integer, some power, such that sigma to that power of I is j. Okay, so that's how the relation works. I is related to j if you can apply sigma enough times to I so that you get j. And the statement is that that's an equivalence relation. All right, so let's try to prove that. Let's try to give a proof of that theorem. I'll just remind you out loud here, an equivalence relation, we have to show that it's reflexive, symmetric, and transitive, right? We need to show that this thing is reflexive, symmetric, and transitive. So let's do them one at a time. Reflexive, we choose an arbitrary element of I. So take any index, all right? Remember in this proof, maybe I should have started, in fact, let me back up a little bit because I want to emphasize that we're going to fix a permutation in Sn. It's not going to change throughout the whole proof. It's not a variable. This equivalence relation depends on sigma. In fact, maybe even better notation, but it would be a little bit rococo to write it if I wrote a sigma near the equivalence, because if you change sigma, you're going to change the equivalence relation. So let's fix a sigma. And now let's pick an index. Okay, and my goal is to show that, so I'm going to use my favorite acronym here, want to show that I is related to I. Okay, so that basically means I need to be able to say, well, what is the M? What power of sigma is going to send I to itself? Well, if you want to send I to itself, you want the identity, right? You want the identity. So I can take M to be 0. If I take M to be 0, then sigma to the 0 is the identity. In a group, anything raised to the 0th power is the identity. So sigma to the 0 of I is, well, it's the identity on I. That's I, right? So this shows that I is related to I, and this is reflexive. 2/3 of our equivalence relation proof, or excuse me, 1/3 of our equivalence relation proof is done. It's reflexive. Cool. Now we got to show it's symmetric. For symmetric, we take two indices, right? Assume that I and j are two indices, and I'm going to assume that I is related to j. My goal, right? Let's do it again. Want to show j is related to I. Want to show that. Okay, well, what does it mean if I is related to j? If I is related to j, well, that means that sigma to the m of I is equal to j for some integer m, right? For some integer m. Now we have to find some integer m that's going to send j to I. So why don't I try to write this a little bit neater in the middle of the page here? If sigma to the m of I is equal to j, then I could certainly apply the inverse of sigma to the m to both sides of that equation. Yeah, the inverse of sigma to the m is just sigma to the minus m, just rules of exponents like in any group, right? That's what's sort of nice here, is that these elements are complicated, they're permutations, but in terms of the group theoretic notation, yeah, the inverse of sigma to the m is sigma to the minus m. Okay, well, on the left-hand side here, sigma to the minus m undoes sigma to the m, so you get I. And on the right-hand side, well, I'm not really going to do anything. I have sigma to the minus m, but minus m is an integer. So that precisely shows that j is related to I, and hence this thing is symmetric. All right, so now we're 2/3 of the way down of our equivalence relation. We've got a reflexive, we've got it symmetric. Finally, we got to show it's transitive. For transitivity, you got to have three indices. So I'll let I, j, and you guessed it, k, pardon me, not be elements of Sn. There are three elements of my index set, three elements of the things that I'm applying this relation to. And let's assume that I is related to j and that j is related to k. Okay? Well, let's write down what that means. Well, first, we want to show, keep the style of the proof consistent. I want to show that I is related to k. That's my goal for transitivity. Well, let's write down what we've got. If I is related to j, then that means that sigma to the m of I is equal to j for some integer m. And likewise, if j is related to k, well, then sigma to the, I'm running out of letters. I can't use n. I'm going to use an L. Sigma to the L of j is k. Right? So now we have to come up with the power of sigma that's going to map I to k. And maybe you should pause the video and kind of think before I say it. Can you come up with it? If you want one more hint before you pause, you just got to kind of think about these things. You have to apply sigma m times and it will transform I into j. Okay? If you apply sigma L times to j, it'll get you to k. So how to start at I and get to k? Pause for dramatic effect. You see the power of sigma I'm going to look at? I'm going to look at sigma to the L plus m. Sigma to the L plus m of I, by rules of exponents, is sigma to the L of sigma to the m of I. Yeah, but sigma to the m of I, we said, is j. And sigma to the L of j is k. So L plus m is certainly an integer because L and m are. So that shows that our relation is, sorry, I should be a little bit more consistent, the style of the proof. So this shows that I is related to K, and hence this is transitive. Okay, so that's the end of the proof. Like I say, this is kind of a setup for something next time. When we meet in class on Monday, if you're able to join us, you can ask me about this proof, or you can ask me about what it's setting up. But I'm going to save that for the next video lecture, and I'm going to end this video now, hopefully keeping it short enough that you'll watch it. Okay.